All right, so we're going to talk about boundary conditions on the wave function. So our wave function, capital Psi, you recall from the separation of variables technique, we said that's little psi is function of r times phi, a function of t, and we know what the time dependence is, what phi is. So this is psi, little psi of r times e to the negative j e over h bar t. All right, so keeping that in mind, we'll end up really getting boundary conditions. Boundary conditions are spatial boundary conditions. End up getting boundary conditions on little psi of r. First one is not a boundary condition in the normal sense of solving partial differential equations. But it comes out about because we interpret the wave function at its square magnitude as a probability density. So because of, and we've said this before, that if we integrate over all space, the absolute value squared of our wave function, this is equal to 1. So this is our normalization. We're calling it a boundary condition here. It's a requirement. Now, because the square magnitude of capital Psi is in here, this is only, and we're integrating in space. Well, let's look at this. This is psi star psi, capital Psi, and that would be little psi phi star. All right, and so this is little psi star little psi times phi star little phi. This would be the square magnitude of little psi. And then here we have phi. So the complex conjugate of phi is e to the j e over h bar t, and then phi is e to the negative j e over h bar t. Well, that's 1. So the square magnitude of capital Psi is equal to the square magnitude of little psi. So this means that we're going to normalize little psi. This is why last time we said we could set the magnitude or the scale factor of phi to be 1. That works out to be convenient, letting it equal 1, then we only have to normalize little psi. So integrating over all space of the square magnitude of little psi, that's equal to 1. All right, normalization. We integrate the psi star psi, the little psi, over all space, that's equal to 1. And that really means physically that the particle exists somewhere in space. Our next boundary condition, and we're going to do this in terms of little psi. So psi of r must be finite. That is, it cannot be infinite anywhere. Has to be single valued, which kind of makes sense. So it actually is a function. And it has to be continuous. So we have some conditions on psi, in addition to normalization. We also have some conditions on the derivative of little psi, and we'll typically be working in Cartesian coordinates. So I'm going to express this in terms of Cartesian coordinates, that the partial of psi with respect to a coordinate variable, say x, y, or z, the partial derivatives must also be finite, single-valued, and continuous. Well, the one caveat on this last part about it being continuous. The partial derivative of little psi with respect to the spatial variable must be continuous when the potential function, the potential energy function V of r is finite. We'll look at a case where V is not always finite, and where it is not finite, then the derivative can be discontinuous. These are really postulates, you might say, but they do have there are some reasons behind these being required. The normalization, as we said, is required because of the interpretation of the square of the wave function's magnitude is a probability density. So this justifies the normalization boundary condition. It also means that psi has to be finite and single valued because this also is required, and also the uncertainty principle will be violated if this was not the case. On the partial derivative, the derivative of psi, we know that this relates to momentum because of the momentum operator. And because momentum must be finite and single valued, the derivative of psi is going to have to be finite and single valued. And for the energy and the potential to be finite everywhere, then this is going to also have to be continuous. All right, so to repeat, we've got our normalization, the integral over all space of the square of the wave function, magnitude squared of the wave function has to be equal to 1. The wave function psi of r has to be finite, single valued, and continuous, and its derivatives, first derivative, has to be finite, single valued, and it's continuous where the potential energy is finite. Now we're going to continue on next and consider almost exclusively one-dimensional situations, one-dimensional solutions, problems for the Schrodinger equation. So we'll be looking at situations where the spatial dependence is only in x. And we'll pick up there next time.